Dear students, welcome to EPG Pathshala. I am Dr. Y.S. Rajput, Emeritus Scientist working at National Dairy Research Institute, Karnal. Today, I will be teaching you capillary gel electrophoresis. Capillary gel electrophoresis is different from many other electrophoretic techniques. That is, it is different from the agar gel electrophoresis, it is different from polyacrylamide gel electrophoresis, and also different from the isoelectric focusing. It has many features which are not present in other electrophoretic techniques. These include the separation time is only in minutes, whereas other electrophoretic techniques takes hours. The resolution power is very high. That is, if sample is applied in low volume, this is of course true for this particular technique, and that's why the sensitivity is very high. Resolution combined with sensitivity is the unique feature of this capillary gel electrophoresis. So we will see that how this technique works for the separation of not only the large molecules such as proteins, but it also works for the small molecules. If we see and compare with other electrophoretic techniques, other techniques are used for separation of macromolecules such as proteins only. So that way, this capillary gel electrophoresis is unique, that one can separate the small molecules, one can separate the large molecules. Here in this case, we will see that the voltage applied is very large. That means heat generated in the system is also very large. But this carefully taken care in the capillary gel electrophoresis that the heat generated is quickly dissipated, and that's how the resolution power is very high. So because of these features, we will discuss this technique in detail, the scientific principles in behind it, because scientific principles in capillary gel electrophoresis are slightly complicated, and my effort will be to simplify this concept in my presentation. First objective is to make you understand the principle of capillary gel electrophoresis. This objective will be discussed at length so that you fully become conversant of advantage of capillary gel electrophoresis over other electrophoresis techniques. Other objective of my presentation is to make you familiar how the technique of capillary gel electrophoresis is performed. Added objective is to discuss applications of capillary gel electrophoresis. The technique of capillary gel electrophoresis is also called high performance capillary electrophoresis or free solution capillary electrophoresis or capillary zone electrophoresis. In this technique, the reagents used are in microscale, and that is in microliter, sample size in nanoliter, and time taken for sample analysis is in minutes. The techniques such as phase, SDS phase, isoelectric focusing can be carried out in capillary system. It is a fact that high voltage used during electrophoresis reduces runtime. However, it results in generation of more heat. Generated heat will facilitate diffusion of molecules, and ultimately resolution will decrease. Resolution means how far two different molecules are separated after electrophoretic run. Heating during electrophoresis can also change structure of molecules. Loss of enzyme activity and epitopic structure are good example for damage of molecule from heat. Principle of capillary gel electrophoresis revolves around generation of reduced heat at higher voltage, and this finally results in improved resolution as well as reduced runtime. Capillary gel electrophoresis differs from phase, SDS phase, agar gel electrophoresis in the sense that high voltage can only be used in capillary gel electrophoresis. No doubt, high voltage generates more heat, but in capillary electrophoresis, generated heat is dissipated fast. This essentially is possible in capillary, where surface to volume ratio of fluid in capillary is very large. Large surface area facilitates in dissipation of heat. During the performance of different methods of capillary gel electrophoresis, the analyte is separated on the basis of its migration in applied electric field. The main advantage of using the capillary electrophoresis over the conventional methods using the slab gel is to overcome the heating effects generated during the electrophoresis. This problem can be resolved by performing the electrophoresis in thin capillaries having a small internal volume and large surface to volume ratio. Therefore, heat generated in such capillaries during the electrophoresis can be dissipated efficiently. In capillary electrophoresis, one end of the capillary is dipped in reservoir buffer containing anode, while the other end is dipped in other reservoir buffer containing cathode. Anode and cathode are connected to power supply, which is capable of providing high voltage. Detector is usually located at the cathodic end of the capillary tube. Time taken for one sample to pass through capillary tube is given by the equation T is equal to L square divided by mu V, where L is the length of tube, mu is the electrophoretic mobility and V is the applied voltage. It is clear from the equation that separation time will be more for lengthier tube. In contrast, higher voltage will reduce separation time. Mu will also be different for different molecules, and therefore, different molecules will be reaching detector at different time. This is how the mixture of molecules are separated in capillary gel electrophoresis. The number of theoretical plates in capillary column, denoted by capital N, is defined in terms of equation N is equal to mu into V over 2D, where mu is equal to electrophoretic mobility, V is the voltage applied and D is the diffusion coefficient. More is the number of theoretical plates, better will be resolution. Number of theoretical plates is linearly dependent on applied voltage, and hence more is the voltage, more will be the number of theoretical plates. It may be noted that increase in voltage also reduces retention time. Thus, in capillary electrophoresis, higher voltage will result in better resolution and reduce the analysis time. Number of theoretical plates is also linearly related with electrophoretic mobility, mu. Number of theoretical plates is inversely related with diffusion coefficient of solute in buffer, that is, separated molecules in buffer. Higher voltage can result in more heat, and if heat is not dissipated, it will increase the diffusion coefficient and thus reduce number of theoretical plates and ultimately resolution. Dear students, it should be clear to you that as long as increase in voltage does not result in increase in diffusion coefficient, it will increase the number of theoretical plates and hence resolution. If applied voltage generates heat that is not quickly dissipated, heat generated will be increasing the diffusion coefficient and resolution will be affected. Dear students, you may note it down that number of theoretical plates is not dependent on length of capillary tube. Therefore, lower length capillary can be used. Again, it may be noted that heat dissipated capacity of longer capillary tube is higher than the smaller capillary tube. Therefore, minimum length of capillary which can dissipate heat effectively is required. Let us again consider both equations, that is N is equal to mu into V over 2D and T is equal to L square over mu into V. Mu and D are dependent on sample. Also, column length does influence retention time. Higher electrophoretic mobility as well as applied voltage will increase number of theoretical plates and reduce retention time. Length has no impact on separation efficiency. A smaller capillary tube will not be as efficient as a large one for dissipating heat. Diffusion of solute is also time dependent and larger retention time may end up with poor resolution. Capillary length and applied voltage affect resolution. Lower capillary length will decrease surface area, which may fail to dissipate heat and resolution will be affected. Reduction in capillary length will decrease electrical resistance, and as per Ohm's law, decrease in resistance will increase current and ultimately heat. This will cause poor resolution. For the fixed length of capillary, if voltage is increased, it will result in increased current and hence again heat will be increased. These points are very essential to understand complexity of applied voltage and capillary length on resolution. For understanding electroendosmosis, we are considering flow of liquid through capillary tube made up of glass or silica. Glass contains selenol ion, which is ionizable. It has a pK value of about 3.0 and hence at pH 5 and above, it will exist in dissociated form, that is SiO-. When buffer will flow through glass capillary, its internal surface will have negative charge. Buffer also have anions and cations. Cations from the buffer will bind to negatively charged selenoid ion, and these charges will remain virtually immotile. This negative and positive charge forms layer. All the negative charge on dissociated hydroxyl group is not occupied by cation in this layer, and some of them unoccupied. However, these unoccupied negative charges in this layer have cations above this layer. These cations exist in hydrated form and can move in electric field towards cathode. This is referred as double layer. When electric current is passed through the glass capillary filled with buffer, fluid will move from anode to cathode because of the positive charge in double layer. The cations will move towards cathode, and in doing so, these will carry entire fluid towards cathode. Thus, it should be clear that cations, anions, even neutral molecules will move towards cathode in capillary gel electrophoresis using glass capillary. This is called electroendosmosis. In capillary electrophoresis, migration of ions controlled by electroendosmosis and electrophoretic mobility. Electroendosmosis is responsible for fluid movement from anode to cathode and will carry anions, neutral molecules, and cations towards cathode. Cations carry positive charge, and so under the electric field, these will move towards cathode. Electroendosmosis and electrophoretic mobility of cations will act in same direction, and cations will reach cathode faster than other ions. Anions will tend to move towards the anode, but electroendosmosis will push them towards cathode. Net effect will be migration of anions towards the cathode, but anions will move slowly. Cations will migrate faster than neutral molecules, and neutral molecules will migrate faster than anions, and anions will move slowest. Thus, in capillary gel electrophoresis, cations, neutral molecules, and anions can be simultaneously separated. It may be noted that in absence of electroendosmosis, anions will migrate to anode. Differential rate migration of different cations will be determined by their differences in electrophoretic mobility. Similarly, different anions acquires different migration rate. Dear students, I have so far covered the scientific principles involved in the capillary gel electrophoresis. This is also referred as the high performance capillary gel electrophoresis. Because of this performance, this is unique in the sense and differs from the other electrophoretic techniques. So far I have covered the scientific principles only, but my efforts in the subsequent presentation will be on how the sample is injected. It has a specific device for injection of sample which is different from the other electrophoretic techniques. How we will see that how a molecule can run through the capillary and can get detected. So we will also discuss the detection systems available at the capillary end and how the data can be processed through a data processor so that the final results comes in the form of a plot where peaks are plotted against the retention time. So this will finally help in identification of unknown molecules separated on the capillary gel electrophoresis. Instrumentation is simple. It requires capillary, 2 buffer reservoirs. One is at the anodic and cathodic end of capillary, cathode, anode, power supply, detector and data processor. One end of the capillary tube is dipped in anodic reservoir containing buffer and the other end is dipped in cathodic reservoir. Power supply capable of providing high voltage is required. Electrodes are connected to power supply. Detector is fixed towards cathodic end of capillary tube. Data process is required for converting detector signal into a usable form. The capillary can be made up of glass, fused silica, Teflon or quartz. These are optically transparent. It has 10 to 100 micrometer internal diameter and 300 micrometer as external diameter. Length of capillary is between 10 to 100 centimeter. One end of the capillary tube is dipped in buffer present in anodic chamber, while the other end is connected to cathodic reservoir. Buffer in anode reservoir, cathode reservoir and capillary same. pH of buffer is kept higher than 5.0 to allow dissociation of SiOH. Detector is fixed towards cathodic side of capillary. The detector can be electrochemical, mass spectrometric, fluorescence or UV visible. Detector detects signal as and when sample components reach cathodic end. Then transmitted signals are processed by data processor. Results becomes available in the form of plot which has peaks corresponding to separated molecules at recorded retention time. Thermostating is heat dissipation mechanism which is very crucial for capillary gel electrophoresis. There should be minimum heat gradient between interior and exterior capillary wall. This depends on heat transfer rate between outermost surface of the exterior wall and its surrounding medium. Temperature gradient between interior and exterior capillary wall is about 125 degrees centigrade per millimeter when air is surrounding the medium. Temperature gradient can be decreased to 51 degrees centigrade per millimeter by forced air cooling. Further, with the arrangement of temperature controlled aluminum plates, the temperature gradient can be decreased to 7 degrees centigrade per millimeter. There are several features in capillary gel electrophoresis. Electrophoresis is performed in narrow bore fused silica capillaries of about 25 to 100 micrometer internal diameter. Electrophoresis is carried out at about 30 kilovolts. This creates high electric field up to 500 volt per centimeter across the capillary. High resistance of the capillary limits current generation and internal heating. The number of theoretical plates are very large, that is in the range of 10 to the power 5 to 10 to the power 6. Analysis time is short. A small volume requirement for the sample, and that is in the range of 1 to 50 nanoliter. Electrophoresis operates in aqueous media and thus increases its applications. Buffer in anode reservoir, cathode reservoir and capillary is same. pH of buffer is kept higher than 5.0 to enable dissociation of silanol group. The sample injection is very critical in capillary gel electrophoresis, where 5 to 30 micrometer cubic sample solution is introduced from the anode end of capillary by one of the two methods, that is pressure injection and other one is the high voltage injection. In pressure injection, capillary is removed from the buffer reservoir at the anodic end and carefully placed in sample solution which is present in airtight or sealed container. Another tube provides pressure to sample solution which forces the sample to enter the capillary from one end. Once the sample is introduced into the capillary, it is returned back to the reservoir and then voltage is applied to start the electrophoresis. In high voltage injection, voltage is shut off, then anodic buffer reservoir is replaced by sample solution reservoir. Once the sample reservoir is present in the position of anodic buffer reservoir, then high voltage is applied. This introduces the sample into capillary tube. Again, voltage is turning off, then sample solution reservoir is removed and anodic buffer reservoir is placed in its original position. Voltage is switched on to start the electrophoresis. In capillary gel electrophoresis, high voltage power supply which are commonly used should be capable of supplying voltage up to 50 kilovolt direct current. The high voltage applied across the anode and cathodic end of the capillary tube moves the sample components at a different rate along the length of capillary tube. Here are few examples for detection systems used in capillary electrophoresis. UV detector is most commonly used. Fluorescence detector can be employed for detection of DNA, and this detector possesses high sensitivity. There are several advantages of capillary electrophoresis over the slab gel. High voltage, that is in the range of 5 to 50 kilovolt, can be applied without affecting resolution and structural integrity of sample. This is possible because availability of very effective heat dissipation system in capillary electrophoresis. Capillary electrophoresis requires less sample volume and therefore it results in enhanced sensitivity. Capillary gel electrophoresis exhibits high resolution. Even it can separate the chiral mixtures. It separates the complex mixtures within minutes. This technique is known for its rapidity. Here are some limitations of capillary gel electrophoresis. In free solution, where electro and osmosis flow is advantageous, it can also be a shortcoming as the positively charged proteins or peptides or any other sample components can be adsorbed on inner surface of the capillary wall. This can lead to trailing or complete loss of component during detection. If sample is diluted, even the highly sensitive detectors cannot detect the sample. High voltage used in capillary gel electrophoresis may cause lethal damage to sample if necessary heat dissipation methods are not applied. This technique is very useful for separation and analysis of wide variety of compounds such as amino acids, peptides, proteins, oligonucleotides, DNA fragments, nucleic acids, metal ions, and drugs. Dear students, if I want to summarize capillary gel electrophoresis, I put in different way that in this particular technique, high voltage used, something to the tune of 5 to 50 kilovolt, which is not the case with the other electrophoretic techniques. Because of this reason, the heat generated is very, very large. But in a capillary system, where the volume to surface area is very large, and that helps in dissipation of the heat. And because of that, there is no diffusion of the band and resolution power is increased. So that way, we can see that capillary gel electrophoresis is the method of choice for the electrophoresis for separating the molecules in very short duration, having high resolution, and also we can perform the experiment quickly. Automation has occurred, and so lot of equipments are there which can be used for the producing a good results from the capillary gel electrophoresis. This is now even can be used in coupling form with the SDS phase, with the agarose gel, and many other electrophoretic techniques. But we see that in this particular electrophoretic technique, it also uses the concept of the chromatography, number of theoretical plates, which are very large in this particular technique. So resolution is high and sensitivity is good. So all these features puts advantage to this particular technique over the other electrophoretic techniques. If you have any problems in understanding the concept, kindly contact me. My email is ys_rajput@rediffmail.com.